When I look at a galaxy, even just in an image, I do not see only the bright stars and glowing gas. In my mind, I also see the invisible structure that holds it all together. Dark matter. In this monologue, I want to walk carefully through what we think dark matter is doing to galaxies, how we know it is there, and why this connects all the way out to dark energy and the fate of the universe. I will start with something simple and familiar. Imagine our own Milky Way galaxy. It is a rotating disk of hundreds of billions of stars, with gas, dust, and a central bulge. If we only had Newton's law of gravity and the visible matter, we could make a prediction. Stars closer to the center, where more mass is concentrated, should orbit faster. Stars farther out, where there is less mass inside their orbit, should move more slowly. This is similar to how planets move in our solar system. Mercury, close to the sun, moves fast. Neptune, far away, moves slowly. That is what we expect if almost all the mass is in the bright central region. But when astronomers actually measured how fast stars and gas orbit in galaxies, especially in the outer regions, they found something very different. The orbital speed did not drop off with distance as expected. Instead, beyond a certain radius, the speed stayed almost constant with distance. We call this a flat rotation curve. This is the first key clue that something important is missing from the visible picture. Let me be more specific. In the 1970s, Vera Rubin and others measured the rotation curves of spiral galaxies. They plotted orbital speed versus distance from the center. If the galaxy's mass were mostly in the bright disk and bulge, the curve should rise in the inner region and then fall roughly like 1 over the square root of the distance. Instead, the curves rose and then flattened out. The outer stars and gas were moving too fast to be held in orbit by the gravity of the visible matter alone. If only the visible matter were present, those stars and gas clouds would escape into intergalactic space. But they do not. So there must be extra mass. It must be spread out more broadly than the luminous disk. And it must interact mainly through gravity, because it does not emit or absorb enough light to be seen directly. This is what we call dark matter. Rotation curves are one line of evidence. Another powerful line comes from galaxy clusters. In the 1930s, Fritz Zwicky studied the Coma cluster, a large cluster of galaxies. He measured how fast the galaxies move inside the cluster. They were moving so fast that if the cluster contained only the visible galaxies, their mutual gravity would not be enough to keep the cluster bound. Again, something like missing mass was needed. Zwicky called it Dunkel Materie, dark matter. At the time, this idea did not reshape cosmology. But later, with better data, the same conclusion kept appearing. We also see evidence for dark matter in gravitational lensing. According to general relativity, mass curves spacetime, and light follows the curved paths. If a massive object like a galaxy or a cluster lies between us and more distant galaxies, the foreground mass can act as a gravitational lens. It can bend and distort the images of the background galaxies. By measuring the amount of distortion, we can infer how much mass is present in the lens and how it is distributed. Over and over, lensing measurements show more mass than can be accounted for by stars, gas, and dust. The extra mass follows a smooth, extended distribution around galaxies and clusters. Again, that is consistent with a halo of dark matter. The Bullet cluster is a famous example. It is actually 2 galaxy clusters that have collided. When clusters collide, the hot gas in them interacts and slows down. But the galaxies mostly pass through each other because they are so far apart. Gravitational lensing of the Bullet cluster shows that most of the mass is not in the slowed down gas, but in regions that line up with the galaxies. This suggests that the dominant mass component, the dark matter, passed through the collision with little interaction, like the galaxies did. This behavior is hard to explain with modified gravity alone. It fits naturally if there is a collisionless dark matter component. So we have multiple independent lines of evidence: rotation curves of galaxies, motions of galaxies in clusters, gravitational lensing, the dynamics of large-scale structure, and also the pattern of temperature fluctuations in the cosmic microwave background. All of them point to the same conclusion. There is a form of matter that does not shine, does not strongly interact with light, and yet has mass and clusters under gravity. It makes up about 85% of the matter in the universe. The ordinary matter, made of protons, neutrons, and electrons, is only about 15% of the total matter. Now I want to connect this to how galaxies form and how dark matter shapes them. In the early universe, shortly after the Big Bang, matter and radiation were almost uniformly distributed. There were tiny fluctuations in density at the level of 1 part in 100,000, imprinted in the cosmic microwave background. These small overdensities are the seeds of all later structure. Dark matter, if it is cold and collisionless, begins to fall into these slightly denser regions under its own gravity. Because dark matter does not interact with radiation the way ordinary matter does, it can start clumping earlier and more efficiently. It forms a web-like pattern of filaments, sheets, and nodes. We call this the cosmic web. As time goes on, dark matter collapses into gravitationally bound halos. These halos are roughly spherical structures where dark matter particles orbit in the combined gravitational field of all the others. The halos range in mass from those of small dwarf galaxies to huge clusters. The key point is that these dark matter halos form first, and they provide the gravitational wells into which ordinary gas can fall. The gas cools, condenses, and forms stars. So in the standard cosmological model, galaxies form inside dark matter halos. The dark matter sets the stage and defines the gravitational scaffolding. Numerical simulations of structure formation show this very clearly. If we run a simulation with cold dark matter and dark energy, starting from the initial conditions we infer from the cosmic microwave background, we see a network of dark matter filaments forming. At the intersections of filaments, massive halos form. When we then add gas physics and star formation to the simulations, galaxies appear in those halos. The resulting distribution of galaxies in the simulated universe looks strikingly similar to what we observe in large sky surveys. This agreement between simulation and observation is one of the strongest pieces of evidence that dark matter is real and that it plays a central role in galaxy formation. Within an individual galaxy, the dark matter halo determines the overall gravitational potential. The visible disk of stars and gas sits embedded in this halo. The flat rotation curves I mentioned earlier are a direct reflection of the halo's mass distribution. In many models, the dark matter density is highest at the center and then falls off with radius, but not as fast as the visible matter. So even far from the visible disk, there is still a lot of dark matter contributing to the gravity. That is why the orbital speeds stay high. Dark matter also affects the shapes of galaxies. In the absence of a dominant halo, a rotating disk of stars and gas would be more fragile. Small perturbations could disrupt it more easily. The halo's gravity stabilizes the disk against certain kinds of instabilities. It also helps to keep the galaxy bound against interactions with neighbors. When two galaxies pass near each other, their dark matter halos interact gravitationally. They can merge and form a larger halo. The stars and gas respond to this changing potential, leading to tidal tails, starbursts, and eventually a new galaxy. In this way, dark matter halos merge hierarchically. Small halos merge to form bigger ones. This is called hierarchical structure formation, and it is a key prediction of the cold dark matter model. Even the types of galaxies we see are influenced by dark matter. Massive halos tend to host large elliptical galaxies or big spirals. Smaller halos tend to host dwarf galaxies. The number and distribution of satellite galaxies around a big galaxy like the Milky Way are sensitive to the properties of dark matter. For example, if dark matter were warm instead of cold, meaning its particles had higher velocities in the early universe, it would erase small-scale density fluctuations. That would lead to fewer small halos and fewer dwarf galaxies. Observations of dwarf galaxies and their dark matter content are being used to test these possibilities. There are still puzzles at the scale of individual galaxies. One is the cusp core problem. Simple simulations of cold dark matter predict that the density of dark matter should rise steeply toward the center of a halo, forming a cusp. But observations of some dwarf galaxies and low surface brightness galaxies suggest that their central dark matter density is more constant, forming a core. There are two broad ways to address this. One is that baryonic physics, like supernova explosions and stellar winds, can push gas around and through gravitational coupling reshape the dark matter distribution. The other is that the nature of dark matter itself might be slightly different from the simplest cold, collisionless picture. For example, self-interacting dark matter could scatter and redistribute in the center. At the moment, this is an active area of research. It is a reminder that even though dark matter works extremely well on large scales, we are still refining our understanding on small scales. Another related issue is the missing satellites problem. Early simulations with cold dark matter predicted more subhalos around galaxies like the Milky Way than the number of satellite galaxies we actually observed. Later, deeper surveys have found more faint dwarf galaxies, which helps. Also, not every dark matter subhalo needs to form many stars. Some halos might remain dark, with too little gas to light up. Improved simulations that include more realistic baryonic physics also reduce the tension. But the exact match between predicted substructure and observed satellites is still being tested. Again, this is where dark matter's role in shaping galaxies becomes a precise probe of its properties. So far, I have talked mostly about dark matter, but the universe also contains dark energy, which acts very differently. Dark energy is not clustered in halos in the same way. It appears to be a smooth component of the universe that causes the expansion of space to accelerate. We infer its presence from observations of distant supernovae, from the large-scale structure, and from the cosmic microwave background. In the Standard Model, dark energy is often modeled as a cosmological constant, an energy density of the vacuum that does not dilute as the universe expands. How does dark energy connect to dark matter and galaxies? On small scales, inside galaxies and clusters, dark energy's effect is negligible. Gravity from matter dominates. But on very large scales beyond clusters, dark energy becomes important. It counteracts gravity and drives the accelerated expansion. This affects how fast structures can grow. In the early universe, when matter density was higher, gravity from dark matter could efficiently pull matter together and form halos. As the universe expands and matter thins out, dark energy becomes more dominant. The growth of new structure slows down. In the far future, if dark energy remains like a cosmological constant, the expansion will continue to accelerate. Existing bound structures like galaxies and clusters will remain bound, but new large-scale structures will not easily form. The cosmic web will slowly freeze out in comoving coordinates. This means that dark matter has done most of its work in shaping galaxies and the cosmic web in the first several billion years. Dark energy controls the long-term evolution of that structure. It sets the background spacetime in which dark matter halos live and merge. Together, dark matter and dark energy define the large-scale geometry and fate of the universe. Dark matter pulls structure together. Dark energy pushes the universe apart. From a spacetime point of view, we can think of dark matter as curving spacetime locally, creating potential wells where galaxies can form. Dark energy, if it is a cosmological constant, can be thought of as a property of spacetime itself, giving it a kind of uniform curvature that leads to accelerated expansion. Einstein's field equations connect the two. The distribution of matter and energy tells spacetime how to curve, and that curvature tells matter how to move. Dark matter and dark energy are just two different contributions to the stress-energy content on the right-hand side of those equations. Even though dark matter is invisible, we can map its distribution statistically through gravitational lensing. Weak lensing surveys measure tiny distortions in the shapes of millions of background galaxies. By averaging over many lines of sight, we reconstruct the projected mass distribution in the foreground. These maps show the cosmic web of dark matter, with filaments and nodes where clusters live. Galaxies preferentially lie along these filaments, tracing the underlying dark matter. This is direct observational evidence that dark matter shapes where galaxies are, not just how they rotate. On smaller scales within a single galaxy, we use stellar motions, gas kinematics, and sometimes strong lensing to probe the halo. For the Milky Way, we measure the motions of stars in the disk and in the stellar halo, as well as the orbits of satellite galaxies and globular clusters. From this, we infer that the Milky Way sits in a dark matter halo that extends far beyond the visible disk, perhaps out to a radius of a few 100,000 light-years. The total mass of this halo is several times larger than the mass in stars and gas. So when we say the Milky Way in a gravitational sense, we are mostly talking about its dark matter halo. It is important to be honest about what we do not know. We do not yet know what dark matter is made of at the particle level. It might be a new kind of elementary particle, such as a weakly interacting massive particle, or WIMP. It might be an axion-like particle, or something more exotic. Many experiments on Earth are trying to detect dark matter particles directly by looking for rare collisions with atomic nuclei in ultrasensitive detectors. So far, there is no confirmed detection. There are also indirect searches, looking for signals from dark matter annihilation or decay in space. Again, no clear signal has emerged. This lack of detection rules out some models and parameter ranges, but many possibilities remain. There are also alternative ideas that try to explain galaxy rotation cluster curves and clout dark matter by modifying the laws of gravity. One example is modified Newtonian dynamics, or MOND, which changes how gravity behaves at very low accelerations. Some of these theories can fit galaxy rotation curves quite well. However, they often struggle to explain all the evidence at once, especially the cosmic microwave background, large-scale structure, and systems like the bullet cluster. At present, the simplest model that fits the broad range of data is still the one with dark matter plus dark energy, within general relativity. But it is scientifically healthy to keep testing gravity itself, because that is how we might discover something deeper. The fate of galaxies in the far future depends on both dark matter and dark energy. If dark energy continues to act like a cosmological constant, the expansion of the universe will keep accelerating. Distant galaxies beyond our local group will eventually recede faster than light relative to us. Not because they move through space faster than light, but because space itself expands between us and them. They will cross our cosmic event horizon and become unobservable. Our local group, including the Milky Way and Andromeda, is gravitationally bound and will remain together. Over very long timescales, dark matter halos will slowly lose energy through processes like gravitational interactions between substructures. The inner regions may contract, and the outer regions may evaporate. Stars will burn out. The baryonic content will cool, but the dark matter halo will still define the gravitational potential of the remnant structure. If dark energy is not a simple cosmological constant, the story could be different. If its density grows with time, we could end up in a Big Rip scenario where even bound structures are eventually torn apart by the accelerating expansion. If it decays, the expansion could slow or even reverse in a big crunch. Current data are consistent with a cosmological constant, but the error bars still allow small deviations. Measuring the properties of dark energy more precisely is one of the main goals of modern cosmology. It is another way in which the large-scale fate of galaxies is tied to the physics of spacetime itself. When I put all of this together, I see a coherent but incomplete picture. Dark matter shapes galaxies by providing the gravitational backbone on which they form, rotate, and evolve. It determines their mass profiles, stabilizes their disks, influences their mergers, and sets their place in the cosmic web. Dark energy shapes the large-scale expansion history, controlling when and how structure can grow and what the ultimate environment of galaxies will be. Gravity and space-time connect these ingredients into a single dynamical system, the universe. We have strong, converging evidence that dark matter exists and that it plays this structural role. We understand its gravitational behavior well enough to simulate galaxy formation and match many observations. Yet we do not know what dark matter is made of, or why dark energy has the value it does. So I end with a focused, open question that sits right at the heart of how dark matter shapes galaxies. When we finally identify the particle or field that makes up dark matter, will its detailed microphysics force us to revise our current picture of galaxy formation and structure? Or will it simply confirm that the invisible scaffolding we have inferred from gravity is exactly what it appears to be?